All right, welcome everyone to the fourth installment of TAPIRS, and today we're very happy to have Rohit Nagpal speaking, and his title's on the screen, so you can just read it. So go ahead, Rohit.
Thanks, Andrew. Thanks for giving me this opportunity to speak, and thank you all for being here. So I'm going to be talking about representation stability for homology of certain arithmetic groups and their applications. So let me start by recalling the definition. So we have the setup is the following. We have a sequence of groups or topological spaces, and we say that they satisfy homological stability if for each ith homology group we have a stability in N eventually. So this is the definition of homological stability, and representation stability is just a somewhat more sophisticated version of this. And instead of giving you the definition of representation stability, I will just explain it using an example later. We usually also have some sort of inclusion maps between these groups, and these isomorphisms between homology groups are induced by these inclusions, right? So let's see an example. So our goal is to relate this to number theory and quantum codes. So let's start with an example. So this is an easy example to understand. The homology of the first homology of the n symmetric group is just z mod 2 as n is large. And this just says that the first homology of the symmetric group stabilizes. So homology, it has stability, at least for the first homology. So, so recall that the first homology of a group is just the abelianization. So G mod its commutator subgroup. And the proof of this theorem is pretty easy because we know the commutator of the symmetric group is the alternating group. And so the first homology is just Z mod 2, right? Generalizing this, Nakaoka showed that homology, any ith homology of symmetric group actually stabilizes for n bigger than or equal to 2i. From what we know these days, this is a pretty easy theorem to prove, and maybe I will sketch a proof of this later in the talk. And just a remark here that these maps, the isomorphism maps are actually just induced by the inclusion of the symmetric group Sn into Sn plus 1. Right. Let's see an example of some other examples. So here we have example GLNR. It also satisfies homological stability. This is due to van der Kallen. Unipotent groups for when R is a S arithmetic ring. This is what I'm going to concentrate later during this talk, and this is a pretty interesting case that I'm going to explain. This is due to Collinet. And there are some other examples: braid groups, mapping class groups, automorphism groups of free groups. And we also have some examples of topological spaces like configuration spaces and Hurwitz spaces. So now let's see an example of a representation stability. So let gamma n be the congruent subgroup of GLN R, where the label is I. So gamma n R comma I. Here's a nice theorem of Lee and Scarba, which says that the first homology of the nth congruent subgroup, the label of label P, is just this little SLN FP, which is just the trace zero matrices, n cross n trace zero matrices over FP, right? Here I'm assuming n is at least 3 and prime the P is odd, right? So so let's see a few things about, let's notice a few things about this. So the dimension of this trace zero matrices is growing like n square minus 1. So this group does not satisfy homological stability, right? But we should notice that the description is uniform in n, right? The first homology is just the trace zero matrices, right? So it doesn't really require n to say this whole thing. So So we should think of that as an example of representation stability where it's uniform in N. There are several ways to formalize representation stability depending on the situation. Here we need to use something called, for example, FI modules or spect stability to formalize this. So I won't say much about that right now. Another interesting thing to note here is that if you take the first homology of the congruent subgroup, then it has a very interesting pairing. So here S2N is the space of weight to level N holomorphic cusp forms. And it's a pretty interesting pairing. But I don't think, so I think the result is basically saying that when N is large, the first homology is so simple that it's number theoretically not interesting. But anyway, I'm going to go over the proof because it has a really nice feature that I want to point out. So let's see the proof of this theorem. So the proof we start by just constructing a map from the source to the target. So we want to show that the abelianization of this group gamma and this congruence of group is the space of trace zero matrices. So there's a well-defined map where we just subtract the identity and then divide by P, because all the other entries are multiples of P. Right, so we want to make sure that this is a well-defined homomorphism. So this is not very hard to see because all the eigenvalues of this matrix A minus I over P are algebraic integers. And we know the product of the eigenvalues is going to be just 1. So this 1 plus P lambda I is the eigenvalue of A, right? So from that, we see that the these sum of lambda I is 0 mod P. And so that just tells us that this is a well-defined homomorphism, right? So we can easily verify surjectivity of phi. We know the trace zero matrices are generated by these elements, where this Eij bar just stands for the matrix whose ijth entry is 1, and all other entries are 0, right? So these are the is generated by these. So all we have to do is construct matrices that actually under phi goes to these things, and they're pretty easy. You can just construct them. So here in the next 2 lines, I'm giving the construction. It's pretty easy to come up with these, right? So surjectivity is there. So far we have proven this. It's pretty easy to see that the kernel of phi is just the congruent subgroup of level P square because of the construction A minus I over P, and if there is another, if the entries are divisible by P squared, they will all be 0 mod P, right? After dividing by P, right? So the next part that we need to do is we need to show that this level P square congruent subgroup is a subset of the commutator subgroup, right? This is actually the hard part of the theorem. So let's see how this is proven. So so for this, we need to use a nice result due to Bass, Milner, and Serre, which says that the level P square congruent subgroup is just consists of elementary matrices, right? So here ENZI is the normal subgroup of the congruent subgroup generated by these identity plus Tij, where T is congruent to 0 mod I. Right, so we should think of this theorem as just saying that congruent subgroup contains enough elementary matrices. And that's pretty much the theme of this talk. Later, I'm going to talk about things where I'm going to talk about certain algebraic groups where we do not have enough elementary matrices and how to handle that situation.
Rohit, wait, this is the part where you need that n is greater or equal to 3, or?
Yeah, I think that's where we need n at least 3. Yeah, I think I forgot to check the range here, but yeah, we do need n bigger than equal to 3. So, and that this might be the place where we need that. Right. Okay. So yeah. So we should think of this result as saying that the congruent subgroup contains enough elementary matrices. And using this, it's pretty easy to finish the proof. To finish the proof, what we do is we just check these things, that the p squared congruent subgroup is equal to the elementary subgroup of this I equals p square, which is contained in its this commutator, which is pretty easy to check, which we can do by just checking on the generators, I think. And this is contained in that. So, and this basically finishes the proof using the exact sequence we saw before, right? Okay, so next. So next is so we saw an example of representation stability. A particular example, this actually generalizes that any ith homology of congruent subgroup is actually stable in n. So again, I don't want to talk about the defined representation stability formally. So you should think of this as it having uniform description in n, right? So some remarks. So how is this theorem proven in general? So this theorem is proven, it's actually based on a result of Charney, which, so Charney's work actually proves homological stability for these groups, where we take Sn semi-direct, the congruent subgroup. And so to prove representation stability, we need some additional setup. And for now, I would say that all the hard part is actually just already contained in Charney's work, because we know all these Fi modules very well now. So we will concentrate only on the homological stability part. Right. Another thing that I want to mention is that Charney also essentially makes an essential use of the elementary matrices while proving her result. So we want to try to see what happens later. We will try to see what happens when we do not have a lot of elementary matrices to deal with, right? Okay. So let's see some applications. So here is an application that I want to talk about. This is an application to completed cohomology. So, or completed homology. I've said completed cohomology in the title, but I've defined completed homology here. So what you can do is you can take these towers of congruent subgroup of increasing level, PR. So this is a decreasing sequence of groups, right? And you can take its homology and take an inverse limit, right? This inverse limit is called completed homology. You should think of this as basically, so what happens when you take the limit, it can take the torsion classes, torsion homology classes, and patch them up and make some non-torsion homology class. So it's a pretty nice way of creating some non-torsion classes using torsion classes. Right. So the result that we have about these homology groups is that these completed homology groups are also stable in n. And this theorem actually uses representation stability for congruent subgroup that I mentioned earlier. So we can think of this as an application of representation stability. So Caligari and Emerton also related these completed cohomology groups to arithmetic and some well-known conjectures in number theory. Right. And another thing that I want to mention is that using completed cohomology, Frank Caligari found a way to prove the following result, which says that the second, which actually calculates the second homology of the congruent subgroup, right? And says something about the dimensions of the ith homology groups. It's basically saying that this theta notation is basically saying that the growth of these homology groups is like n to the 2i. So it's they're all non-trivial for n large enough, right? Right. So we do not really know that we have seen the first homology groups as the trace zero matrices, and then we know the second homology groups as well. I don't think we know a general formula for the third or higher homology groups of congruent subgroups. So that's pretty hard, I guess. Right? So I want to note an interesting thing about this proof of Caligari's. It's that, so what they have done is that they have leveraged stability, the homological stability or representation stability, to prove non-vanishing, which is a potentially very useful strategy. And I'll try to explain later how this can be useful, right? Okay, so next I'm gonna explain some applications to quantum codes. Right, so here's a definition of a Ramanujan graph, right? So Ramanujan graphs are regular graphs. So if you have a d-regular graph with n vertices, it's Ramanujan if it satisfies this spectral condition that its eigenvalues are either plus or minus d, or their magnitude is smaller than 2 square root d minus 1. Right? So right, so I'm gonna say why they are important later. So let me actually start with like how to construct such graphs, right? So here is a way to construct Ramanujan graphs. You take the local field, the QP, and string of integers inside it, which is O. And you take the group G PGL2 over F and its maximal compact subgroup K. Then if you take the Brouhart-Titz building, building for this group, which is just G mod K in this case, it is a P+1 regular tree, right? So it's already giving you a way to think about regular trees, but now we want something finite because Ramanujan graphs have to be finite. So what you do is you take a discrete co-compact subgroup and you mod out by its action on this Brouhart-Titz tree. And what we get is a finite P+1 regular graph, right? So this is a really nice way to construct finite regular graphs, but we also need to verify the spectral condition, which may not be true for arbitrary things. So here is a result of Lubotsky, Phillips, and Sarnak, which says that if gamma is a congruent subgroup of an arithmetic group, of an arithmetic lattice of G, then this quotient is Ramanujan. And this was a pretty like famous result. It has a lot of applications. I think it used some result of Deligne, which says that some infinite dimensional spherical representations are tempered. So it uses pretty like sophisticated machinery to, they use this result, for example, right? And they also concluded some really nice properties of these Ramanujan graphs. Something about their girth and chromatic number. They have very high girth and high chromatic numbers, and these are the best known examples of this. And another useful thing about Ramanujan graphs is that we can use them to construct really efficient error correcting codes. That's what I'm gonna get to next.
Rohit, sorry. Did you say what the nodes and what the edges are? I don't think I completely understand that.
So I think you should think of nodes as lines inside. Um, so P plus one regular. So you should think of the vertices of these Brouillard-Titz tree as just the lines inside the, the projective space, two-dimensional projective space, I think. And there is a edge between them. If there is, like, you can go from one line to the other using some sort of elementary operation, right? So, but anyway, Brouillard-Titz buildings, you should think of the simplices as something built out of subspaces of these projective spaces. Is it making sense?
Yeah, sort of. Thanks.
Right. Okay. Right. So Ramanujan.
On Peter's question, so like this is like different than the fairy graph or something.
This is different than which graph?
Like the fairy graph or something.
Oh, the fairy graph. No, yeah, when we are talking about buildings over a local field, I'm not sure how to relate this to fairy graphs at all. Right. So yeah, it could have some relation, but I'm not sure. Right. Right. So we can use Ramanujan graphs to construct really efficient error correcting codes. And there are some higher dimensional versions of this which can be used to construct quantum codes, right? So that's what I'm gonna describe a little bit about them. As we have seen for Ramanujan graphs, you can construct Ramanujan complexes by taking finite quotients of Brouillard-Titz building for certain algebraic groups, right? It's pretty hard to define Ramanujan complexes, so I'm not really going to define. So it has some spectral condition, like in the Ramanujan graphs, they satisfy some spectral condition, but they also need to satisfy some other properties, like they're called co-systolic expansion and systolic expansion. There are some things that they satisfy. So you can't take arbitrary algebraic groups and take their finite quotients to construct Ramanujan complexes. They have to be like, they have to have some properties, right? So so one of the things so now let me actually just try to give you a construction. So here's a construction of a Ramanujan complex. This is communicated to me by Shai Evra. And I also just found out like a couple of days ago that Shai Evra got Ramanujan prize last month for some of this work. So which is interesting. So here is what you do to construct a specific Ramanujan complex. So what you can do is you take the field F, which is the field Q adjoint square root of -1, and let O be the ring of integers inside it, and U and F be the nth unitary group over F corresponding to the Euclidean Hermitian form. So my Hermitian form is the one whose matrix is just the identity matrix. And of course, the Hermitian operator is just coming from the complex conjugation, right? And then you take the congruent subgroup of label P inside UN O1 over Q. So you have to invert Q, and then you can take the congruent subgroup like this. Then the quotient of the Brouillard-Titz complex for the this unitary group is a Ramanujan complex, right? So it's a generalization of the example that we saw earlier, right? Now let's go to the next one. So one thing to note that we want this Ramanujan complex to be finite. So we want so let's go back again. So we are quotienting by UN this, which I'm calling the unitary congruent subgroup, right? Because the congruent subgroup of the unitary unitary subgroup, the group of unitary matrices, right? We want this to be co-compact inside UNFQ, right? So I think this follows from the fact that UN is compact at infinity in some theory of algebraic groups. So that's one of the reasons why we have to stick to some weird groups, and we can't just work with general linear group, right? Okay, so next I want to explain like what to do with these Ramanujan complexes. So here's the main theorem, which says that if you have Ramanujan complex, or actually if you have any complex, then you can construct a code, a quantum code, if you know that the ith cohomology is non-zero and it has some systole and co-systole condition, right? And the parameters for this code are going to be length, distance, and dimension. They are parameters of a quantum code, right? So let's not go too deep into that, but the main point is that if you are starting with the Ramanujan graph, then it satisfies all these conditions about co-systoles and systoles already. So for this theorem to work, we need to just know that the non-zero ith cohomology, we have non-zero interesting cohomologies, right? So that's what I'm getting at. We constructed one Ramanujan complex, and if we could say something about its cohomologies, then we should be able to construct some interesting quantum codes, right? And in fact, these quantum code is going to be very efficient, like most efficient quantum codes that we have so far, if we can apply this theorem to the Ramanujan complex that I just mentioned, right?
Oh, Rohit, there's a question in the chat for you.
What is M? M? Oh, so this is theta of M. Theta of M would just say that, okay, yeah. I mean, M is just a parameter, which is just saying that the size is M. You can just say the complex is of size, instead of saying exactly M, it's just saying growing like M. I think it's just coming from how you code the size. That's what I think of it. I don't really understand the whole, this whole theorem very well, but yeah, it's just the size of the complex in some sense. Right. Okay, so, right. So we need to, let's try and see if we can do something with it. So all we have to do is just make sure that we have interesting non-zero cohomologies of this Ramanujan complex that we constructed, which we constructed by quotienting by the action of the congruent subgroup, the unitary congruent subgroup. But here's a hurdle. The unitary congruent subgroup has no interesting non-trivial rational cohomology. So, and Brouhard-Titz complexes are highly connected. So this is what we exactly need to use this theorem that we just mentioned, right? I mean, it doesn't have to be rational cohomology. We need some cohomology. So, but the first thing to do is like try to see if we can get rational cohomology that we can't, right? So let me explain why this is true, why the unipotent group doesn't have any interesting rational cohomology. So here's a very general result, and the setup is this. If you take a non-Archimedean locally compact field and a simple semi-simple algebraic group over K of, and let L be the K rank of L, K rank of G, and gamma be any discrete co-compact subgroup of GK, then the rational cohomology of gamma is 0 in all dimensions except 0 and L, right? So it's basically saying that this result does apply to the congruent subgroup of the unitary group, the unitary congruent subgroup that we have been talking about, because we saw for finiteness we need the inclusion of this inside the UNF to be discrete and co-compact. So this theorem applies, and so That's why we don't have any interesting relational cohomology, right? So we can't rely on relational cohomology. So, but maybe there are some integral cohomologies or mod P cohomologies that we can construct, right? So that's the next thing that we want to try and see. So here is, we go back to Frank Caligari's strategy, which says that if you can prove stability, then you can leverage these completed homologies to prove non-vanishing, right? Frank Caligari pointed to us that this actually holds in this situation as well, and you can actually do this. That means if we can prove homological stability for these SN semi-direct congruent subgroup, unitary congruent subgroup, then we will have a non-trivial lower bounds. And if we have non-trivial lower bounds, we will have very efficient quantum codes, as I explained later. Right. So far, this is just a conjecture. Right. So I want to point out that this is a much harder than Charney's result, for example, because we don't really have a lot of elementary matrices inside the unitary congruent subgroup. So that's basically the problem here. Since we don't have elementary matrices, like how to even deal with such a case, right? Oh yeah, so that's the remark. Yeah. Okay, so next, maybe I will tell about some other applications where you can use stability. Here is the application that I want to say of this homological stability result. So here's another homological stability result. You take the orthogonal group. Here, the orthogonal group ON just corresponds to the orthogonal group which with signature 0 N0. That means the form corresponds to the identity matrix, or it's a Euclidean orthogonal group, right? Euclidean orthogonal groups also doesn't have a lot of elementary matrices, right? But we do have stability for them, which is pretty interesting. So the proof of this is very different from Charney's proof, and I will explain later. I'll give some examples, or at least try to explain how this is proven, right? Okay, and Collinet also used this stability result to prove some, did some calculation about this this BO space. So these are some K-theoretic things, and calculated these homotopy groups for these, which is interesting, right? Right. So here there is some hope that even if there are not enough elementary matrices, we can prove stability, and that's what I want to get to next. So how do we prove homological stability? Let's get to the proofs now. So let's take a sequence of group, and we want to show homological stability for them, and we can do that if we can find some triangulated spaces xn for each n, and an increasing sequence of integer which grows at least faster than 2k plus 1 with the following properties. The first is the acyclicity. We want the triangulated space xn to be highly acyclic. Second is that we want the group Gn to act transitively on low dimensional simplices. Right. Right, or t less than equal to n minus 1, right? And we want a stability condition, which is basically saying that the stabilizer of a simplex, if you take a simplex and take a stabilizer, it should be a conjugate to a smaller group in this sequence of groups. And some other formal conditions. GLOW is some global stabilizer of a simplex, and is also, if it stabilizes globally, then it stabilizes pointwise. And this permutation condition, which is saying that you can permute in some ways. Here, okay, I want to point out this permutation condition is actually one of the reasons why Charney's result applies to the symmetric group, semi-direct product, the congruent subgroup, because congruent subgroup doesn't have the symmetric group inside it. So you can't do this permutation inside it. So that's one of the reasons why Chinese result applies to symmetric group, semi-direct congruent subgroup, right? Okay, so the general result is that if you can find a triangulated space with these properties, then the groups have stability, right? So all these conditions hold and we have stability. And proof goes back to Quillen, but this formulation is due to Collinet. And proof is kind of just analyzing some spectral sequence. You just take relative cohomologies, you apply this derived functor, or actually a relative version of it. So it's kind of a relative cohomology spectral sequence, and you just argue by induction. That's all it takes to prove this stability theorem, right? Okay, so let's see an example. Let's prove Nakaoka's stability theorem. So here is a nice triangulated space. So I want to define the space whose k-simplices are just sequences x0 to xk of mutually distinct numbers from n, right? It's a pretty easy space to define. So it satisfies the acyclicity condition. Xn is n-2 acyclic, right? This is easy to prove using induction, but I can also, I will probably also mention how to prove it. It's pretty easy. So Farmer's acyclicity of complex tells us that these sequence of spaces satisfy acyclicity, and all other conditions are pretty easy to prove. The hardest condition in that sequence of conditions that I said is the first one, acyclicity, and the other ones are actually quite easy to prove. So this Xn and Fk equals 2k plus 1 satisfies the conditions of the stability theorem. So we have proved Nakaoka's theorem, right? Okay, so let's see another example. So let's see how to prove homological stability for O and Z. So let's take Q be the standard Euclidean quadratic form which correspond to the identity matrix. And now let's define this Stiefel complex for corresponding to this. So here, here x0 to xk is a k-simplex if these are just mutually orthogonal elements in Zn, right? And it's an unordered tuple. So k-simplex is an unordered tuple of k plus 1 mutually orthogonal vectors in Zn, right? Okay, so I want to say that then Yn is homotopy equivalent to n-1 sphere Sn-1, right? Okay, maybe I should have said these are also of norm 1. So I think I forgot to mention these. All these xi's are also of norm 1. So they are just like plus or minus any of the basis vectors, right? Any of the standard basis vectors, basically. Right, and the proof of this theorem that this is homotopy equivalent to a sphere is pretty easy. It's basically saying that you argue by induction, you know that if you take the all the simplices which do not have En or En-1, these E1, E2, En is the basis, standard basis vectors, then that's a n-2 sphere by induction. And then what you're doing is just adding on like the link of En and minus En is just homotopy equivalent to this smaller one, right? So you just get a suspension of this Sn-1. It would have been easier if I could draw a picture, but I can't because these are slides. But yeah, that's basically the proof. And then you can define another complex Xn where these for the same space I'm talking about. Now what I'm doing is like I'm getting rid of I'm adding order to it. First, I was taking unordered pairs. Now I'm defining k-simplices to be these sequences of mutually orthogonal unit length elements in the end, right? It's pretty much related to the previous complex that I said. And there is a nice map from xn to yn, which forgets the ordering. And the fibers are pretty nice for this map. So it's a highly connected map. And so you can prove that xn is highly acyclic using that, right? Because the yn was highly acyclic. And so we get to the, we can prove the homological stability for these orthogonal groups using that. Right? Again, we are just applying the stability theorem. And as I said, the hardest part is just to prove the acyclicity condition, right? Okay, so let's see some other cases. So this stability theorem could be proven, could be used to prove different kinds of results. Right, so like for example, Hatcher and Vogtmann used surf theory to prove high acyclicity for some complexes and used a result similar to the stability theorem to prove homological stability for odd Fn. And you can do this for many other groups, right? Right, so Charney used some elementary matrices to prove her complex is highly acyclic. So that's where, I mean, so I was saying that Charney's proof essentially boils down to using the fact that there are enough elementary matrices, and she used this fact that there are enough elementary matrices to actually prove her complex is highly acyclic, and she constructs like some complex for congruence, right? Okay, now let's get back to the case when we do not have a lot of elementary matrices, and what we can do in this case. So here is an example. We take, so ONZ, we started the ONZ, Vogtmann's result, which was not very interesting because it's a finite group, because they are just like n factorial times 2 to the n many vectors that you can have in a or yeah, so it's a finite group, right? So it's not very surprising, but in general ONR is pretty hard, and I want to point out that it is much harder in the split case. The split case is the one where the signature is NN. We already know that the split case, in the split case, these O and N are satisfy homological stability basically for any Noetherian ring R, right? And this basically boils down to having enough elementary matrices, which you can see from the following result. So here it's saying that if Gn is a compatible sequence of hyperbolic unitary groups, for example, the split orthogonal group or these symplectic groups, then eventually the commutator agrees with the group of elementary matrices. So it's basically saying that we have a lot of elementary matrices, right? Okay, but in general, this is very hard, the anisotropic case, when the signature is n, 0. And that's why this result that I mentioned earlier as well is a pretty interesting result, right? Colin also proved this another result. You can work with either the orthogonal group or the unitary group, and they satisfy homological stability here. And you should also notice that I'm using this S arithmetic rings, right, instead of just Z, because over Z, it's the first one is not even interesting. And another reason for using S arithmetic rings is I should mention it now, that it's basically because we are going to use strong approximation theorem, and there's a version that is due to Nasser. It's called Nasser's strong approximation theorem that works over these S arithmetic rings, the localizations of these ring of integers, right? Okay, so let's see how this is proven. I'm running out of time soon, I guess. Right, so here's the group. Now we want to try to apply the stability theorem to this. Right, so if you want to try to apply the stability theorem, we need to construct some complex, right? And the complex is again very similar to the one that we saw for symmetric group or the orthogonal group earlier. So what we do is we define the case implices to be the sequences x0 to xk of mutually orthogonal unit length elements in this localized ring, like nth dimensional, like to the n, right? Yeah, so that's very similar to what we did for symmetric groups or the orthogonal groups, right? All we need to do is we need to prove that this is highly acyclic, right? Okay, so now let's see how to do that. So to do that, I'm gonna talk about general strategy. So the general strategy says that if you have some sort of orthogonality relation, which I'm just assuming is a symmetric relation, satisfying x part y implies x not equal to y, right? That's all we need for this relation. And if we construct a triangulated space whose case implices are these sequences x0 to xk, right? Then there's a very easy way to prove that this complex is going to be highly acyclic. All you need to do is given any 2k plus 2 elements in the set, you can, if you can find another vector which is orthogonal to or perpendicular to all of these, then SE is k acyclic, right? Right, so that's a really nice acyclicity criteria, and it's basically boils down to some sort of this nerve-Poisson theorem. It's not a very hard theorem to prove, right? And let me point out that Nakaoka's theorem, the complex that we constructed, the Farmer's complex, you can pretty easily prove this. Like if you have 2k plus 2 mutually distinct element, you can take y to be a number distinct from all of them, and so we will get the high acyclicity of that complex, right? So applying this to our xn, what we need is exactly this to prove high acyclicity. Given any 2k plus 2 unit length elements in this ring, Rn, R is this ring, so in Rn, if we can construct a unit length element which is perpendicular to each one of them, then xn is highly acyclic, right? Okay. So next, let me rephrase this problem. This is a completely number theoretic problem now. It's just rephrasing that same problem. We need to construct this unit length vector perpendicular to a given set of unit length vectors, right? And this actually is proven using the strong approximation theorem and Hasse principle. First, what you do is you construct y locally for each localization, and then you patch them up using Hasse principle and the strong approximation theorem. And that basically proves that xn is highly acyclic, and we get homological stability for this unitary group, right? Yeah, so this is how you tackle the case when you don't have enough elementary matrices, right? I guess I should stop here. So I'm running out of time, so I'll stop here.
All right, thank you, Rohit, for the nice talk. Okay, are there questions?
So in this kind of this conjecture you were talking about earlier for the unitary congruent subgroups, so do you expect there to be a maybe, let's say, in the case where your S arithmetic ring is such that the map to the finite unitary group is surjective, do you expect some sort of like, unitary version of VIC to act on these the homology of the congruent subgroups?
Well, we could, yeah. Even I mean, even they are going to be FI modules, even because the way I chose things, I made sure that instead of n, I had a prime p, which is inert in the Gaussian integers, and if it's inert in the Gaussian integers, the corresponding finite unitary group is actually just a general linear group, and you can check that that contains. I mean,
so that's where the inert.
That's why the inert. That's why I chose it to be inert. So it's going to be a FI module, and there's no problem with that.
I see.
Can I also ask something? So you said that knowing that you have representation stability let Caligari deduce some non-vanishing result. Could you say something about that?
Yeah, that is pretty okay. So this argument for, I mean, they're pretty different arguments in the unitary case and in the usual congruent subgroup of general linear group case. They're completely different. I mean, very different actually. This one, the unitary one, probably shouldn't talk about because it's like came from a personal communication and you might want to do something with it. But you can see how they did it in the usual case, the general linear group case. So I think they also had to use some K-theoretic knowledge to do that. It's not coming from free. So and I think one of the things that they use is one of the main tools is the completed homology spectral sequence, which relates completed homology to the usual homologies, which is one of the main tools that they use. And they had to analyze that to get those lower bounds. Yeah, so the main tool is completed homology spectral sequence plus K-theory.
All right, I'm gonna stop recording now.